that is the homework 3. Okay, and then the follow-up is called talk about the stability. So that could be another homework. Okay. So right now today I'm going to have this one, steady state error. So here we talk about is so the first one is I want to define what is the steady state. Okay, steady state simply is we concerned about the value of the system when time approaching to infinity. That's called the steady state. Okay. And what is error? Error simply is in terms of our notation using EF of S. So basically, here steady state error is limit t approaching to infinity of E of S, and in our controls we're using E as a common notations. Okay, error at the steady state, so that is a common notation for steady state error. So this error basically we can calculate, and what is the error definitions? Usually error definition is this. If you remember our closed loop, so this is our input and positive and negative. So here is something. So here content can be a very complicated system, and the feedback from the output here, so that is C over S. And the feedback here can contain any kind of the sensors. Okay, so let me just make up one here. Okay, so whatever the contents here, that is make up this control loop. So usually we define the error is the comparisons of the R to this feedback here. Okay, and this one I'm kind of confusing people now. This is the definition of the error, okay? But in particular here for the steady state error, I want to clarify about this one. In particular, this error is the comparison between the input and output, which means between the command and our response. So here, let me precisely define. This error is the description between the R and output. So this is our command or input, and this is our output in particular. Okay, so this is the what we define the error, and we want to study steady state error because we want to know exactly, eventually, how far our output away from the input. So maybe the best way to describe the steady state error is this. If I change this one into the unitary feedback here, then this configuration exactly fit into this. Okay. So again, when we want to calculate steady state error, basically we simply want to calculate the eventual discrepancies between the input and output. Okay. So here I hope we unify the language we talk about here. So from whatever the system we can always calculate. So how to determine this one? Basically here you can see C over R is our transfer functions. Whatever the configurations of the block diagrams, we should be able to come up with the transfer functions by all means. Okay, you can look up the configurations, or you can apply the Masson's rule, and you can always get this one. Okay, so once you have the transfer functions, and let me define this one as GS. So here you can see, therefore, from here C equal to G times R. Okay, so therefore, if we want to calculate the error, and error by definition is R minus C, and this one, let me tailor it a little bit. So that means I have R times 1 minus C over R. Okay. Okay, so basically this one is equal to R times 1 minus G. So if we have a transfer functions, then we can have this one be calculated by this. That is R of S times 1 minus the G of S, 1 minus transfer functions. That's a function of S. Will be good? So this is a very generic formula. Okay, depends on the transfer function, we simply plug into here. So there's no unique way to describe, so simply we take out this one. And also, we can, with this concept, the steady state, this concept already, we can also apply the concept, say, if we want to calculate the steady state response, of CT. Okay, so basically that one is equal to limit t approaching to 0, then we simply calculate the value of CT there. Okay. Or you want to say, I want to calculate steady state of something something, you simply plug in that definition to there. Okay. So we can look at one example here, and so for example, C over R equal to 1, let me make a 1, so say S squared plus 2S plus 1, okay. So we want to calculate, let me say define E of S equal to R minus C. So that is R times 1 minus C over R, so that is R times 1 minus 1 S squared plus 2S plus 1. So that is R of S times S squared plus 2S plus 1 S plus 2S. Okay. So here we want to determine the steady state error. So that is infinity E of S. We plug in here. Oh, holy cow. I'm so stupid. I'm so stupid. I can do it. So here, I'm going to correct some of my descriptions here. Sorry, I didn't follow up my notes closely. I'm sorry. The stupid thing is, here I combine the time domain with the S domain. When we do the calculation, I found no, it's not doable. Okay. Let me modify and without too much. Okay, so here I use blue to edit up more information. So this is the definitions, and once we take the plus inverse of the ES, and that is become E of t, right? So basically here, rather than using this, we have to work on of E of t here. Okay. So basically here, this one won't be good. So let me delete it. So continue on this. So this is the time proportion to infinity of E of t. And this value, if you remember in our Laplace transform table, that basically is equal to, do you have that table with you? Let me take our last one.
Is this the final value theorem?
Yes. So here we applied is called the final value theorem. Okay, check out on your table, on your handouts, that will be equal to limit as approaching to 0 s times e over s. So where we can apply. Okay, so here in the concept, in the fundamental definition of the steady state, that means we're concerned about the time approaching to infinity, and that infinity about the time functions. Then ET, then we can apply the Laplace transform theorem. So we have this one, we apply this theorem, basically this one, description in the time domain is equivalent to the description in the S domain like this. Okay, good. And this one is useful, that one is what I'm going to use. Okay, so basically this is E over S. So if you like, you can box these information. Basically that's successful. So basically right now we are using this is E of S, we can apply it. Okay, so let me continue this example here. So basically here, let me modify this to be E of T. Okay, so that one should be equal to limit as approaching to 0 s times E over s. Okay, so now we continue. So limit as approaching to 0 s times, and then we plug in E of s by this equation here. So that is s3 plus, s2 plus 2s s squared plus 2s plus 1 times r over s. Good. Okay, then we can begin to do some calculations. So from here, can you see? Depends on. Let me make out a few examples here. So the input, say the unit impulse. Then R of S will be equal to 1, right? And then this is our ESS. So with this one, when RS equal to 1, I'm going to take advantage of the whiteboard. When this one equal to 1, so the whole thing will be equal to, look at this carefully, numerator equal to 0, denominator become 1. So basically this value equal to 0. Okay? So when this is the unit step input, then Rs equal to S over 1. So that means this one is 1 over S. Okay, so this one is 1 over S. Then again, we can do this one. So this one, the term, this one is cancelled out, right? Then again, when S equal to 0, numerator becomes 0, denominator equal to 1, this is still 0. And unit ramp, this is square, so that is square. Okay, so for this case, this one you can see we cancel squared as squared from the numerator. Basically, let me write it up one more time. So that becomes s plus 2 s squared plus 2s plus 1, right? You see? So basically this is 0.5. So the steady state error appeared when the input become the unit ramp. So this basically is just like this. The unit step is the input pretty much, I would say is constant. The unit ramp is the input pretty much fast, okay? And if you want to continue, say, unit parabola, so basically that is like this. This is equal to 1. This is t, and this t squared, something like this. Okay. And this is an impulse. So here is graphically. Like this one, you can double check this is S3 and 1 over. Okay. Basically, you can see this will go to infinity. So we have 2 minutes. So with this exercise, for example, if this would be a system, the system behaves like that, and you like to have a system to track this kind of input, just like this, the system will respond very exactly, go to 0. So that means eventually the system response will just like the eventual response of this one. For the unit step input, the input is something like this. Eventually that unit equal to 1. So with this analysis, you can guarantee the systems eventually, I don't care about the transient, but eventually the system will be something like this. The transient, I don't care. The transient, not I don't care. We can deal with separately by the previous example, the influence of initial conditions. Okay. And the same thing for the unit ramp input. So this is a unit ramp. Okay, so this is a T, so this is a 1. So again, we can skip off the transient. Eventually, the system will be something like this, and the magnitude is 0.5. You good? And the other one, if given this system, this input is like this, then this system have the error become infinite. Basically, the system behavior, we know the behavior will be like this. So from here, the system is kind of linearly behave, but the input is polynomial growing. Basically, the error become larger and larger. So if you imagine this would be the very primitive jet plane. If you be the pilot, if you want to do certain gesture control, you better not to use this primitive plane to do any quicker motion like this. Otherwise, you're going to, the people will sing the national theme for you. You know, basically that meaning the system will become unstable and out of control, either crash or something. Okay, so with this concept, we talk about a certain system is fast, certain system is slow. For this system can be as fast as these features, but won't be fast as this one. Okay, so next time we're coming back, we will talk about another quantitative method describing the features of the system, and pretty much based upon this. Okay, thank you.